The pelican. It is a bird we all seem to know. We see them gliding in perfect formation along our coastlines, their impressive wingspans silhouetted against the setting sun. We picture them perched on old wooden piers, their long bills tucked neatly against their chests, waiting patiently. They are a constant and reassuring presence in many parts of the world, from tropical lagoons to temperate shores. The distinctive shape of their bill, the famous pouch beneath it. They are a beloved part of our coastal landscapes, a living symbol of the sea's enduring rhythm and its abundant life. But how well do we truly know these magnificent birds? Beyond their familiar outline, a world of extraordinary secrets is waiting to be discovered. We often see them as simple, almost comical figures, especially when they waddle on land or swallow a fish with a great gulp. Yet, this perception hides a creature of remarkable sophistication and design. The pelican is a master of its environment, an avian engineer whose every movement is governed by profound physical principles. To truly understand the pelican, we must look beyond what we think we know and venture into a realm of hidden mechanics and ingenious adaptations. This journey will take us deep inside the world of this seemingly ordinary bird. We will go beyond its feathers and skin to explore the science that makes its life possible. How does it fly with such effortless grace, carrying its heavy body for hundreds of kilometers? How does its strange baggy pouch actually work to catch slippery, fast-moving fish? And how can it possibly dive from great heights, crashing into the water at high speed without suffering any harm? These are not simple questions, and the answers are far from obvious. Our exploration will reveal the pelican as you have never seen it before. We will peel back the layers of familiarity to uncover a marvel of natural engineering. This is a story not just of a bird, but of forces, pressures, and the beautiful mathematics of survival. We will examine the physics that shapes its flight, the fluid dynamics that govern its hunt, and the biomechanics that protect it from harm. Prepare to see the pelican not just as an animal, but as a living, breathing testament to the power of evolution and the elegance of physical law. Our investigation begins with one of the pelican's most defining features, its extraordinary bill, the gular pouch that hangs beneath it. This is not just a simple scoop. It is a highly specialized multifunctional tool perfected over millions of years. When a pelican dives, this pouch expands dramatically, engulfing not just its prey, but also vast amounts of water. How does it handle the immense forces involved? The sheer weight of the water alone is immense, yet the bird manages this delicate and violent maneuver with incredible precision. This is a question of fluid dynamics and complex engineering. The spectacle of a plunge-diving brown pelican is truly breathtaking. It folds its wings and plummets from the sky like a feathered arrow, hitting the water with a tremendous splash. From heights of up to 20 meters, it accelerates towards the surface, reaching speeds that would be fatal for most other creatures. How does it survive this impact? Time and time again. The answer lies hidden within its anatomy. Special air sacs under its skin, a reinforced neck, an instinct for the perfect entry angle, all combine to mitigate the brutal forces of the collision. It is a masterclass in managing energy and pressure. Flying also presents its own set of physical challenges. A pelican is a large and heavy bird, and getting airborne, especially with a belly full of fish, requires a huge amount of energy. Yet, we see them soaring for hours, seemingly without effort. They are experts at exploiting the physics of the air around them, by riding on rising columns of warm air, known as thermals, and by flying in precise formations to reduce drag. They have mastered the art of energy conservation. We will explore the mathematics of lift and drag that allows these heavyweights of the sky to become such efficient, long-distance travelers. In this film, we will bring this hidden world to life, using high-speed cameras, advanced graphics, insights from scientific archives. We will decode the secrets of the pelican. We will overlay diagrams onto live footage to show the forces at play. We will calculate the energy required for flight and the stresses endured during a dive. This is the story of the pelican told through the language of physics, a journey that reveals a creature far more complex and fascinating than its familiar silhouette suggests. We will see how every aspect of its being is a solution to a physical puzzle. For a bird as large and heavy as a pelican, flight is a constant battle against the relentless pull of gravity. To understand how they conquer the skies, we must first look at the fundamental forces at play. Every time a pelican takes to the air, it is managing a delicate balance between two opposing pairs of forces. Weight, which must be overcome by an upward force called lift. Lift is generated by the movement of air over the specially curved surface of the pelican's wings. Thrust, the forward propulsion generated by flapping its wings, which must fight against drag, the resistance of the air pushing back on the bird. The secret to a pelican's sustained flight lies in its ability to generate sufficient lift to counteract its considerable weight. The shape of its wing, known as an airfoil, is crucial. As the pelican moves forward, air flows faster over the curved upper surface of the wing than it does across the flatter bottom surface. According to a principle of physics discovered by Daniel Bernoulli, this difference in speed creates a difference in pressure. The pressure above the wing becomes lower than the pressure below it. This pressure differential results in a net upward force, pushing the wing and therefore the pelican into the sky. It is a subtle but powerful effect, turning simple air movement into a force capable of lifting these avian heavyweights. Of course, generating lift is only half the story. The pelican must also contend with drag, the ever-present force of air resistance that seeks to slow it down. Drag comes from two main sources: friction from the air moving over the bird's body and wings, and the turbulence created as the air is displaced. To fly efficiently, a pelican must be streamlined, minimizing the surface area that pushes against the air. Its sleek body, the way it tucks its feet back during flight, and the smooth surface of its feathers are all adaptations designed to reduce this resistance. Flapping its wings provides the necessary thrust to overcome drag and maintain forward momentum, but this action requires a significant amount of energy. The interplay between these four forces, lift, weight, thrust, and drag, governs every moment of a pelican's time in the air. When a pelican glides smoothly at a constant altitude, lift is perfectly balanced with its weight, and the minimal thrust it gets from its forward motion is balanced by drag. To climb, it must increase its lift, perhaps by changing the angle of its wings or flapping more powerfully. To slow down for landing, it adjusts its wings and body to increase drag. Understanding this continuous dynamic dance of forces is the first step in appreciating the pelican, not just as a bird, but as a master of aerodynamics. The wings of a pelican are not just simple feathered limbs. They are marvels of biological engineering, shaped by millions of years of evolution to be highly effective and efficient. One key characteristic we can measure is the wing loading. This is a simple ratio: the bird's weight divided by the total wing area. A pelican has a relatively high wing loading compared to smaller birds, so each square centimeter of wing supports more weight. That makes taking off harder. Often a running start is needed to reach liftoff. Once airborne, high wing loading lets pelicans fly faster and ride out gusts. Another key metric is the aspect ratio. This is the ratio of the wingspan to the wing's average width or chord. Pelicans have long, broad wings, a moderately high aspect ratio. High aspect ratio wings, like an albatross, are ideal for long ocean glides. Low aspect ratio wings, like a sparrow, are for agile turning. Pelican wings are a compromise: long enough for soaring, broad enough to carry heavy loads and maneuver along coasts. They use two flight modes. First, flapping flight, thrust for takeoff, climbing, and crossing calm air. It's the powerhouse mode, with deep, powerful strokes. You can see the deep, slow, and powerful strokes as it labors to get airborne from the water's surface. Second, gliding. Wings held stiff to use momentum for lift, descending slowly. It's the energy-saving mode for long trips. Pelicans seamlessly switch and combine these modes. They flap to gain altitude, then glide when they find wind or thermals. By adapting constantly to conditions, they minimize energy use. Their wing design makes them efficient aerial hunters and coastal travelers. To truly appreciate the pelican's prowess in the air, let's try to estimate the lift force a pelican needs to generate. The formula for lift is relatively straightforward. It depends on the density of the air. It depends on the wing area. It depends on the square of the velocity. And it depends on the lift coefficient, the wing shape and angle. An adult brown pelican can weigh around 4 kilograms. That means its wings must generate about 39 newtons of lift to stay level, with a wingspan of up to 2 meters and a wing area of around 0.6 square meters. We can calculate the speed it needs to fly. Plugging in the numbers, cruising speed is around 10 to 15 meters per second, or about 36 to 54 kilometers per hour. This aligns perfectly with observations and data from GPS tracking studies. These studies, some of which are documented in archival scientific journals, we've fitted pelicans with tiny electronic trackers to monitor their movements. The data reveals they routinely cover hundreds of kilometers in a single day, maintaining these impressive speeds for hours on end. The mathematics confirms what we see with our own eyes. The Pelican is a powerful and efficient flying machine engineered to cruise the coastlines. But how efficient is it really? We can compare the energy cost of transport for a pelican with that of other seabirds. Scientists measure this in terms of joules of energy expended per kilogram of body mass, per kilometer traveled. For a bird of its size, the pelican has a remarkably low cost of transport, especially when it is able to utilize gliding and soaring. Its energy expenditure during gliding flight is only slightly higher than its baseline metabolic rate when at rest. This means that once it is airborne and finds the right conditions, it can travel vast distances for very little more energy than it would use just sitting on a pier. This incredible efficiency is a product of its size and its specialized flight strategies. Larger birds are inherently more efficient at gliding than smaller birds, as they lose altitude more slowly for every meter they travel forward. The pelican is perfectly positioned in terms of size to take maximum advantage of this physical principle. When we look at the numbers, the pelican is not just a bird flying, it is an organism that has optimized its body and behavior to solve the complex energetic equation of flight. Every long, lazy glide is a calculated move in a grand strategy of energy conservation. One of the pelican's most elegant energy-saving techniques is its mastery of soaring. Soaring allows a bird to maintain or even gain altitude, effectively getting a free ride from the atmosphere. Pelicans are experts at a particular type of soaring called thermal soaring. This involves finding and circling within columns of rising warm air known as thermals. Thermals are formed when the sun heats the ground, which then heats the air directly above it. This warmer, less dense air rises, creating an invisible elevator in the sky. Pelicans with broad wings and keen senses are adept at locating these columns. When a pelican finds a thermal, it begins to circle within it. By staying inside the column of rising air, the bird is lifted upwards, often to great heights with almost no effort. We can see them, sometimes in large groups, circling higher and higher until they are just specks in the sky. Once they have gained sufficient altitude, they can peel off from the thermal and glide for long distances, slowly trading stored potential energy for kinetic energy and forward motion. They glide in the direction they want to travel until they've lost too much height, then seek out another thermal to begin the process again. This climb and glide technique is a cornerstone of long-distance travel. Another, more subtle form of soaring over the ocean is dynamic soaring. It exploits the difference in wind speed between the air near the water and the air higher up. Near the surface, friction with the water slows the wind down. Higher up, the wind is much faster. Pelicans use this wind gradient to gain energy. They dive down into the slower air near the water to gain speed, then turn and climb back up into the faster wind, gaining a boost of speed and altitude. This creates a graceful, undulating flight path just above the waves. This mastery of the air is not learned in a day. Young pelicans spend time observing their elders, practicing these complex maneuvers. They develop an intuitive feel for the invisible movements of the atmosphere, learning to read subtle signs of a thermal or favorable wind gradient. This is not just instinct, it is learned and passed down. By harnessing free environmental energy, the pelican transforms flight into an artful dance with the wind, both beautiful and exquisitely efficient. Perhaps one of the most iconic sights along our coasts is a line of pelicans flying in perfect formation, often just inches above the waves. This is not merely a matter of social order. It is a highly sophisticated, cooperative strategy to save energy. The most common formation is a single file line, but they are also frequently seen in a V formation, similar to geese. This precise arrangement is a brilliant solution to the problem of drag. The physics behind this is fascinating. As a bird flies, the movement of its wings creates rotating vortices of air that trail off from the wingtips. The air on the outside of the vortex is pushed downwards, which is what the bird pushes against to create lift. The air on the inside of the vortex spirals upwards. By positioning itself correctly, the bird behind can fly in this region of upwash. This upward moving air helps to support the bird, effectively giving it a small lift. This means the bird doesn't have to work as hard to stay airborne, reducing the energy it needs to expend on flapping. Studies have shown that birds flying in formation can reduce their energy expenditure by a significant amount, with estimates ranging from 10 to as much as 30%. The birds in the formation are constantly making tiny adjustments to their position to stay in the sweet spot of the upwash from the bird ahead. This requires incredible skill and concentration. Often, The birds will take turns at the front, as the lead bird has the most demanding job, flying in undisturbed air with no aerodynamic advantage. This rotation of the lead position ensures that the burden is shared and the entire flock can travel farther and more efficiently. This cooperative behavior highlights that the pelican's mastery of flight physics extends beyond individual skill into the realm of group dynamics. They have effectively learned to manipulate the airflow, not just of their own wings, but of the entire flock. This behavior is a testament to the power of collective effort in the natural world. Each pelican in the line is not just a passenger, but an active participant in a complex aerodynamic system, working together to make the long journey a little easier. It is a beautiful example of how physics and social behavior can intertwine to create a strategy for survival that is both elegant and profoundly effective. Having explored the marvels of their flight, we now turn our attention to the pelican's most iconic feature, its bill and the extraordinary gular pouch that hangs beneath it. This is more than just a beak. It is a precision-engineered instrument, a multifunctional tool that serves as a fishing net, a dinner plate, and a cooling system. When we watch a pelican, our eyes are immediately drawn to this strange and wonderful apparatus. Its sheer size relative to the bird's head seems almost comical at first glance. Yet, in the world of physics and survival, this pouch is a masterpiece of evolutionary design, perfectly adapted for the pelican's unique method of hunting. The primary function of this remarkable structure is to catch fish, but it does not function like a simple scoop or a bucket. The pelican's strategy is far more sophisticated. Brown pelican plunge dives. White pelican hunts cooperatively on the surface. The pouch expands with astonishing speed to engulf a huge volume of water and prey. That rapid expansion creates a dynamic pressure field which helps trap fish that might otherwise escape. It's a high-speed, high-stakes maneuver, relying on fluid dynamics, even if the pelican doesn't know the equations. The pouch is not a passive bag, but an active, dynamic trap. Beyond hunting, the pouch serves other vital purposes. After a successful catch, it acts as a temporary holding container, while the bird expels the water it scooped up. This process is a critical step before swallowing the meal. On hot days, pelicans flutter their pouch rapidly. This gular fluttering increases airflow over moist, blood vessel-rich skin, acting like a radiator to dissipate excess heat. The pouch is essential for thermoregulation and a vital adaptation for large birds in warm climates. So this seemingly simple feature is actually a complex biological system solving many physical and physiological problems. It is a fishing net that understands fluid mechanics, a colander that separates solids from liquids with remarkable efficiency, and a personal air conditioner. As we delve into the anatomy and biomechanics of the bill and pouch, we'll uncover the hidden physics that makes this possible. We'll see how its structure withstands enormous forces, and how its use is timed with nanosecond precision, revealing it as one of the most versatile and effective tools in the animal kingdom. To understand how the pouch performs its incredible feats, we must first look at its underlying anatomy. The structure is supported by the two long flexible bones of the pelican's lower mandible. Unlike the rigid, fused jawbone of most birds, these two halves are not fused at the tip. Instead, they are connected by flexible ligaments, allowing them to bow outwards dramatically. This flexibility is the key to the pouch's astonishing expansion. When the pelican opens its mouth to strike, powerful muscles pull these bones apart, stretching the gular skin into a vast bag-like net. The upper mandible, or maxilla, is long and hooked at the end, perfect for securing slippery prey. The pouch itself is a marvel of biological material science. The gular skin is not just loose flesh, it is a highly specialized tissue, incredibly thin yet remarkably strong and elastic. It is composed of layers of collagen and elastin fibers, arranged in a way that allows for massive stretching without tearing. When not in use, this skin contracts and folds neatly against the lower bill, offering little wind resistance during flight. But during a catch, it can expand to hold a volume of water far greater than the pelican's own stomach. Some species, like the Australian pelican, have a pouch that can hold up to 13 liters, or about 3 gallons, of water. The movement is controlled by a complex set of muscles at the base of the jaw. These muscles must act with incredible speed and precision. The decision to strike and the full expansion of the pouch happen in a fraction of a second. This rapid deployment is crucial for trapping fast-moving fish. The force required to open the pouch against the resistance of the water is substantial, and the muscles that power this action are correspondingly robust. Once the catch is made, a different set of muscles, help to control the contraction of the pouch as the water is drained away, a more delicate but equally important part of the process. This combination of flexible bones, highly elastic skin, and powerful, fast-acting muscles creates a system that is both incredibly strong and exquisitely controllable. It is a structure built to handle the violent hydrodynamics of a high-speed plunge. Archival studies on the tissue properties of the gular pouch have confirmed its extraordinary elasticity, showing it can stretch to several times its resting size and then snap back into shape without damage. This anatomical foundation is what allows the pelican to execute its unique and effective hunting strategy, turning its very face into a dynamic and efficient fishing machine. When a pelican executes its famous plunge dive, the pouch and bill are at the very forefront of a violent collision between air and water. The physics at play are immense and complex. As the bird strikes the surface, the timing of the mouth opening is absolutely critical. High-speed footage reveals that the pelican begins to open its bill just milliseconds before impact. This is not a random action. It is a precisely timed maneuver designed to use the force of the water itself to aid in the pouch's expansion. The bird essentially uses its forward momentum to inflate the pouch. Momentum transfer, fluid dynamics. As the bill enters the water, the lower mandible bows outwards. The pouch begins to fill. The sudden deceleration of the bird's head transfers momentum to the water, pushing it into the expanding pouch. The volume of water that rushes in is enormous, and its weight is staggering. A pouch holding 10 liters of water adds 10 kilograms of mass, more than double the bird's own body weight in an instant. The force exerted on the jawbones and the pouch skin is immense. This is known as hydrodynamic drag, a force that increases with the square of the velocity. It is this force that abruptly slows the pelican's head. Its body continues to pivot over it into the water. This process can be modeled as a rapid transfer of momentum. The pelican's head and pouch system, moving at high speed, collides with a stationary column of water. To bring that water from a standstill to being inside the moving pouch, a massive impulse, a change in momentum, is required. According to Newton's third law, for every action, there is an equal and opposite reaction. The force the pouch exerts on the water to scoop it up is matched by an equal and opposite force exerted by the water on the pouch. This is the braking force that stops the pelican's head so suddenly, and is what the bird's anatomy is so perfectly evolved to withstand. The timing of the pouch closure is just as critical as its opening. After engulfing its target, the pelican must close its bill to trap the fish. Then begin draining. This action must also be incredibly fast to prevent the prey from escaping. The dive, the impact, the expansion, the capture, the closure. It is a symphony of perfectly coordinated movements, all governed by the unforgiving laws of fluid mechanics and momentum. Section 4. The math inside the mouth. Calculating the catch. We can use simple physics to put some numbers to the incredible forces a pelican endures. Let's create a basic model. Imagine a brown pelican diving and scooping up about 8 liters of water, which has a mass of 8 kilograms. If the pelican hits the water at a speed of, say, 15 meters per second, 54 kilometers per hour, and the pouch fills in just half a second, we can estimate the average force required. The primary force acting to slow the pelican's head is the drag from the pouch opening and filling with water. The force of drag can be estimated using the drag equation. Density of water, cross-sectional area of the opening pouch, velocity, drag coefficient. Given the large area of the fully expanded pouch, this drag force is enormous. It's like opening a parachute underwater. This force could easily reach several hundred newtons, equivalent to many times the bird's own body weight. These calculations, though simplified, give us a profound appreciation for the strength of the pelican's anatomy. The jawbones must endure immense bending stresses without snapping, and the skin of the pouch must withstand tearing forces akin to those on a sail in a gale. The neck muscles must also absorb the shock of this sudden deceleration to prevent catastrophic injury to the spine. Archival biomechanical studies have used sophisticated computer models and material testing to analyze these stresses more accurately. They confirm that the forces are indeed at the very limit of what biological materials can withstand. These scientific investigations replace our general awe with specific numbers, quantifying the incredible engineering of the pelican's bill. The math reveals that every dive is a calculated risk, a walk on the razor's edge of structural failure, and a testament to the bird's flawless design and execution. The pelican is not just a hunter, it is a high-performance athlete operating at the peak of its physical limits, Section 5. Draining the ocean. The post-capture maneuver. Capturing the fish is only half the battle. Now, the pelican is faced with a new problem. Its pouch is full of water. A pelican cannot swallow its prey while its pouch is waterlogged. It would essentially drown itself. Furthermore, taking off with that much extra weight would be nearly impossible. So, the next critical step is to drain the water while securely retaining the fish. This is a delicate and skillful maneuver. The bird tips its head forward, allowing the water to pour out from the sides of its closed bill. The upper and lower mandibles fit together just tightly enough to keep the fish inside while letting the water escape. This process can take up to a minute, and during this time, the pelican is extremely vulnerable. It is heavy, off balance, and unable to fly. This is often when opportunistic gulls and other seabirds will try to harass the pelican, attempting to steal its catch. The pelican must remain vigilant, often raising its head and threatening the would-be thieves while continuing the slow process of draining. It's a tense waiting game. The pelican uses gravity to do most of the work, simply tilting its bill downwards. It may also gently contract the muscles of the pouch, squeezing the remaining water out like a sponge. Once the water is gone, all that remains is the fish. The pelican then performs the final act of the hunt. It tosses its head back with a powerful flick, throwing the fish from the pouch into the air and catching it headfirst to slide smoothly down its gullet. This maneuver ensures the fish's fins and spines do not get caught in its throat. Violent plunge, patient draining, final, acrobatic swallow. The entire sequence is a perfectly choreographed and physically demanding process. Each step is a solution to a different physical challenge, showcasing the versatility of the pelican's incredible bill and pouch. Section 6. A pouch for every purpose, species and strategies. While the basic design of the bill and pouch is common to all pelicans, there are fascinating variations among the 8 species. The most dramatic difference is between the plunge divers, brown pelican, Peruvian pelican, and the surface foraging species, American white pelican. Plunge divers tend to have slightly smaller, more robust pouches built to withstand massive hydrodynamic forces when they hit the water. Their anatomy is geared toward impact and underwater capture. Great white pelicans, Dalmatian pelicans, American white pelicans. They are cooperative hunters. They do not dive from the sky. Instead, they swim together on the surface, forming a semicircle to corral fish into the shallows. As they herd their prey, they dip their heads in unison, using their huge pouches as fishing nets to scoop up the trapped fish. Their pouches are often larger and more voluminous than those of the plunge divers, capable of holding an immense quantity of water and fish. Their strategy is one of coordination and scale rather than high-impact acrobatics. These different strategies are elegant examples of niche partitioning. By specializing in different hunting methods, various pelican species can coexist without directly competing. The brown pelican patrols the skies, targeting fish near the surface in open water, while the American white pelican works the shallows and inland lakes in organized groups. Each species' pouch and associated behaviors are finely tuned to its specific environment and prey. This diversity showcases the adaptability of the basic pelican body plan. From the high-impact pouch of the plunge diver to the capacious scoop of the cooperative forager, the pelican's bill is a testament to the power of adaptive radiation. It is a single anatomical concept, modified and refined to suit a range of physical challenges and ecological opportunities. By examining these differences, we gain a deeper appreciation for the interplay between physics, behavior, and evolution. The pelican's pouch is not a one-size-fits-all solution. It is a custom-built tool, with each species possessing the precise model it needs to thrive in its own corner of the world. The feathered arrow. The sight of a brown pelican hunting is one of nature's most dramatic spectacles. From a cruising altitude of 10 meters, sometimes even 20 meters, it spots its prey. Then, in an instant, it transforms from a graceful glider into a living projectile. It folds its wings back, points its bill downwards, and commits to the dive. This is not a gentle descent, it is a controlled plummet. The bird accelerates under the constant pull of gravity, its streamlined body, cutting through the air with minimal resistance. This transformation is a masterclass in converting potential energy into the kinetic energy of motion. The higher it dives from, the faster it will be traveling when it hits the water. As the pelican falls, it is essentially a free-falling object, albeit one with some aerodynamic control. The bird reaches what is known as terminal velocity, the point at which gravity is balanced by air resistance, or drag. For a pelican in its diving posture, this speed can reach upwards of 60 km per hour. It has become a feathered arrow, aimed at the heart of the ocean, and its only goal is to strike before its fast-moving prey can escape. The speed serves two purposes. Firstly, it minimizes the time the fish has to react and flee. Secondly, the momentum helps penetrate the water's surface to reach fish a meter or two deep. The bird must accurately judge the position and depth of the fish, account for the refraction of light at the water surface, which distorts its view, and execute a dive that is both fast and accurate. It is a high-stakes, high-speed gamble. A slight miscalculation could result in a missed meal, or, far worse, a devastating injury. Every plunge is a testament to the pelican's extraordinary senses and its innate understanding of the physical forces that govern its aerial and aquatic worlds. It is a hunter that has weaponized gravity itself. The moment of impact, the transition from air to water, is the most violent and dangerous moment of the entire hunt. The pelican hits the water not with a gentle splash, but with a concussive force that sends spray erupting into the air. At speeds of over 60 km per hour, hitting water is not like hitting a soft cushion. Water, at high speeds, behaves more like a solid surface due to its high density and incompressibility. The impact generates an enormous, instantaneous pressure wave that could easily break bones. It could rupture organs. It could cause a fatal concussion. For a human, a dive from such a height without proper form would be catastrophic. Yet the pelican does this dozens, even hundreds of times a day, emerging unharmed. The secret to its survival lies in its entry form. A pelican never hits the water flat. Instead, it strikes with an almost perfect bill-first entry, creating the smallest possible entry profile. Its long pointed bill acts like the sharp bow of a ship cleaving the water. This minimizes the initial impact force by concentrating it on a small strong area. Immediately after the bill, the head, the slender neck follow, creating a narrow channel for the rest of the body. This streamlined entry is crucial for managing the immense pressure and deceleration forces. It's the difference between diving cleanly and belly flopping from a great height. Just before impact, the pelican rotates its body slightly and braces for the collision. The wings are kept folded tightly against the body to prevent them from being wrenched back and broken. The neck is held at a specific angle, allowing the powerful neck and chest muscles to absorb and distribute the shock. The bird is actively managing the collision, turning its entire body into a finely tuned shock-absorbing system. The forces of deceleration are immense. The pelican goes from 60 km per hour to nearly a standstill in a fraction of a second over a distance of perhaps a meter or two. This rapid change in velocity subjects the bird's internal organs to extreme G-forces. The pelican's body is built to withstand this. Its organs are tightly packed and supported by internal connective tissues to prevent them from shifting violently upon impact. The entire event is a marvel of biomechanical engineering, a solution to a problem of high-energy physics that the pelican has solved through millions of years of evolution. Anatomy of a shock absorber. The pelican's ability to survive repeated high-speed impacts isn't just its diving technique. Its anatomy is riddled with hidden protective features. A network of subcutaneous air sacs sits beneath the skin in its chest and underbelly. These sacs are extensions of the respiratory system. Just before impact, the bird inflates them. On impact, those pockets act like biological airbags, compressing and absorbing a large portion of the force. They cushion the blow and protect underlying muscles and bones. The skeletal and muscular systems are highly specialized for this lifestyle. The neck looks slender, but contains powerful muscles and uniquely shaped vertebrae that lock for stability. That reinforcement prevents snapping or hyperextension on impact. The rib cage is exceptionally robust, and the sternum, the breastbone, is broad and strong, shielding vital organs. The torso is built like a reinforced fuselage under extreme stress. Even the pelican's brain is protected. Like a woodpecker that endures repetitive shocks, the pelican's brain is small and fits snugly with little room to move. That tight fit, plus cerebrospinal fluid cushioning, prevents sloshing during violent deceleration. This prevents traumatic brain injury that would otherwise be inevitable. It's a subtle, life-saving adaptation that keeps the pilot of this feathered fighter jet conscious and in control. These internal adaptations, airbags, reinforced bones, and a protected brain are largely invisible to a casual observer. They are the hidden secrets that make the pelican's spectacular dive possible. When we watch a pelican plunge, we're not just watching a bird catch a fish. We see millions of years of evolutionary refinement, a living solution to one of nature's extreme engineering challenges. Each dive is a test of perfectly integrated, shock-absorbing systems. Section 4. The numbers of the dive, calculating the force. To grasp the true scale of the forces involved, we turn to the language of physics. Let's consider a 4-kilogram pelican. The bird dives from a height of 15 meters. Neglecting air resistance, we convert potential energy to kinetic energy. That gives an impact speed of about 17 meters per second, which is roughly 61 kilometers per hour. Now assume the bird comes to a stop over 2 meters after entering the water. A simple kinematic equation gives a deceleration of over 70 meters per second squared. That's more than 7 times gravity, over 7 Gs. To put it in context, fighter pilots experience this only during extreme maneuvers. They wear G-suits to prevent blacking out. The pelican endures this force raw. Newton's second law, force equals mass times acceleration. For our 4-kilogram pelican, the average braking force is around 280 newtons. That's like suddenly supporting a weight of 28 kilograms, 7 times its body weight. These numbers from basic physics are confirmed by more sophisticated methods. Archival full studies document instrumented tags, tiny devices attached to pelicans. The tags contain accelerometers that record the precise forces during dives. The data often shows peak forces even higher than our simple estimates. They reveal the violence of impact and the incredible efficiency of the bird's deceleration. This quantitative view transforms our understanding. It's no longer just a dramatic dive. The pelican is a biological structure, engineered to withstand measurable, predictable, enormous forces. The numbers tell a story of immense stress and exquisite adaptation. Survival on the edge requires not just instinct, but a body built to the most demanding engineering specifications. Section 5. Architects of the coastline. The ecological role. Pelicans are more than just remarkable feats of biological engineering. They are also key players in the coastal ecosystems they inhabit. As top predators in the marine food web, they play a crucial role in controlling fish populations. By preying predominantly on small, schooling fish that are abundant near the surface, they help to maintain a healthy balance in the ecosystem. Their presence and hunting success can be a powerful indicator of the overall health of the marine environment. Conversely, pelicans are also highly sensitive to changes in their environment, making them important sentinel species. A decline in pelican numbers can be an early warning sign of ecological problems, overfishing, pollution, effects of climate change on ocean currents, and fish distribution. The infamous case of the pesticide DDT in the mid-20th century provides a stark example. The chemical accumulated in the food chain and caused pelicans to lay eggs with shells so thin they would break during incubation. This led to a catastrophic population crash, and the plight of the brown pelican became a powerful symbol for the environmental movement. Their nesting colonies also have a significant local impact. By congregating in large numbers on offshore islands or in mangrove forests, they transport vast quantities of nutrients from the sea to the land in the form of guano or droppings. This nutrient deposition can dramatically enrich the soil, supporting unique plant communities and in turn providing habitat for other species of insects and animals. In this way, pelicans act as ecological engineers, actively shaping the landscape and creating biodiversity hotspots. They are a vital link, connecting the nutrient cycles of the ocean and the land. From their influence on fish populations to their role as environmental indicators and nutrient vectors, pelicans are deeply woven into the fabric of their coastal homes. Their story is not just one of physics and flight, but of connection and consequence. The health of the pelican is inextricably linked to the health of the ocean itself. Section 1. The pelican as masterpiece. We began this journey with a familiar bird, a simple silhouette against a coastal sunset. We end it with a creature transformed, revealed as a masterpiece of biological engineering. We have seen that behind every seemingly effortless glide, every dramatic plunge, and every great gulp, there lies a world of hidden physics. The pelican, we have discovered, is not just an animal shaped by its environment, but a living, breathing machine that has mastered the fundamental laws of nature. We have witnessed the economy of its flight. We have delved into the fluid dynamics of its iconic pouch. We have felt the violence of its plunge dive, and we have understood the challenges of its recovery. The Pelican, it turns out, is a finely tuned instrument, each component and every action a testament to the power of natural selection in shaping form and function. Section 2. A never-ending story. Our exploration has taken us deep into the mechanics of this incredible bird, drawing on decades of scientific research. For those whose curiosity has been sparked, the journey of discovery does not have to end here. We encourage you to seek out the work of the dedicated scientists who have spent their lives unraveling the secrets of the pelican, from tracking their epic migrations to modeling the forces of their spectacular dives. The story of the pelican is also a story of our relationship with the natural world. These birds are not distant figures in a wildlife documentary. They are our neighbors. They share our coastlines, our rivers, and our lakes. Their health is a direct reflection of the health of our planet's aquatic ecosystems. As we have seen, they are exquisitely adapted to their environment, but they are also vulnerable to the changes we impose upon it. Pollution, habitat loss, and climate change all pose significant threats to their survival. The story of the pelican is, therefore, a story that is still being written, and we all have a part to play in how it unfolds. By appreciating the complexity and ingenuity of these birds, we can be inspired to protect the wild spaces they call home. The wonder we feel watching a pelican soar is a powerful catalyst for conservation, a reminder of what we stand to lose. Thank you for joining us on this journey into the secret world of the pelican. We hope it has given you a new appreciation for this familiar yet extraordinary bird. If you enjoyed this deep dive into the science of nature and want to see more stories like this, please take a moment to like this video and subscribe to our channel. Your support allows us to continue exploring the wonders of our planet, from the grandest spectacles to the hidden physics that makes them all possible. Join us again as we uncover the next chapter in the never-ending story of life on Earth.